Hello. In the previous lecture, we were discussing something about comparison test. Today also, I'm going to teach you some important questions that can be solved very easily using comparison test. See, this test looks very easy, and you'll find that most of the questions that I'm right now doing, and I did in previous lecture also, were based on this comparison test. Although a slight uh, knowledge of calculus would indeed be very helpful to in order to understand the applicability of comparison test. Again, this is a very short lecture. Please do see this lecture till the complete end. So what do you think about this series? Will this be a convergence series or a divergence series? Okay, and not only comparison test, you can use limit comparison test also. That is also an important test. And otherwise, you can use like root test as well as ratio test. So till now, I have not taught you any other test except all these four tests. So you have to keep in mind at least these four tests in whatever questions right now I am giving you. So what do you think about this particular series? Will it be a convergence series or a divergence series? Let us see. If this is our series, then you see I can write it in form of, so I can write this in form of 2 times sine square 1 upon 2a. And from this, I completely know that, see, what I can do, I know that sine theta is less than theta for all theta lying between 0 and pi by 2. If 0 pi by 2, if I'm just taking because this is positive. So in general, always remember this is the truth for all theta belongs to this. So I know this is 1 upon 2 and as n is taken larger, this will come in the first quadrant. In fact, for n equal to 1, it is half. Half itself lies in the first quadrant. So I can write that sine square 1 upon 2n would indeed be less than 1 upon 2n whole square. And 2 times sine square 1 upon 2n will indeed be less than 1 upon 2n square. Since 1 upon n square is convergent, so therefore this is convergent. Since I'm writing since summation 1 upon 2 times n square is convergent, it implies that summation n equals to 1 to infinity 1 minus cos of 1 by n is convergent. Okay, so this is problem number 1. So we'll do today at a very quick rate, at least 5 to 10 questions, so that this particular test gets embedded in your head that this is an important test. And please remember, people think that more tests we know, then we are going to succeed in this. No, that's not the case. You should know the applicability. So the first thing is take this comparison test very seriously. Try to see whether from certain hints you can compare the given series or not. So let's say this is your question. Okay, so this is ln. ln is, so this is 1 upon n, ln of 1 plus n. Now you see from calculus itself, log of 1 plus x is always less than x. So this is an important result from differential calculus. And if I want to prove it, let me prove it for all f belongs to 0 to infinity to r. And let us consider function equals to ln of 1 plus x minus of x differentiated. What you will get? You will get 1 upon 1 plus x minus 1. And indeed, it would be simply equals to minus of x upon 1 plus x, which is certainly less than 0. It implies that f of x is a decreasing function. Decreasing function for all x greater than 0. So it implies f of x will be less than f of 0. If I'm saying that f of x would be less than f of 0, it implies log of 1 plus x minus of x will be less than f of 0, which is log 1 minus 0, which is again 0. So I can say that log of 1 plus x minus x would be less than 0 for all x greater than 0. So it implies for the cases of natural number, I can clearly write log of 1 plus n is less than 1 upon n. For all n greater than equals to 2. Okay, so indeed I can do this thing. I can write that 1 upon n log of 1 plus 1 upon n can be written less than 1 upon n square for all greater than equal to 2. It implies that summation n equals to 2 to infinity 1 upon n ln of 1 plus 1 upon n will be a convergence series by comparison test. I hope it is clear. What do you think about this series? So always, whenever you have this in power, that is n is in power, try to use root test instead of ratio test. Because if I use a ratio test, if I do an plus 1 upon n, this an plus 1 will lead to increase in this power, and that would be very difficult to uh, find a limit. So basically, if I use a root test, all I need to find is limit n tends to infinity modulus of an raised to power 1 upon n. Let me see what the limit comes out as. So limit n tends to infinity, this will turn out as n upon n plus 1 raised to power n plus 1. And with certainly is equals to limit n tends to infinity 1 minus 1 upon n plus 1 raised to power of n plus 1. The limit turns out to be e to power minus 1 or 1 upon e, which is certainly less than 1. So it implies that by root test, the series given by summation n equals to 1 to infinity n upon n plus 1 raised to power n into n plus 1 is a convergence series. This is from the root test. Okay, now let us do another problem. What can be said about this series? See, what I can do is, in this particular series, raised to power n square. Again, the power is n square. Always in these cases, don't use ratio test. Root test would be very beneficial for these series. See how? If I use root test, see, limit n tends to infinity, n mod raised to power 1 upon n would give me limit n tends to infinity. This is n square plus 1 upon n square plus n plus 1 raised to power n. And with certainly is equals to limit n tends to infinity. This is 1 minus 1 upon n square plus n plus 1. And in fact, I'll write n here and raised to power. Then see, if n is tending to large numbers, if n is large, then n square will be very, very large than n plus 1. So I can write it as simply n square. This is 1 minus n upon n square raised to power n, which certainly is certainly equals to writing 1 minus 1 upon n raised to power n, and which is e to power minus 1, 1 upon e is less than 1. So therefore, by ratio test, so by root test, this series is convergent. Okay. Now, let us consider a few more concrete examples now. Let us take this example for that matter. Summation n equals to 1 to infinity n raised to power 1 upon n minus 1 raised to power n. See, if you remember, we have already proven that n raised to power 1 upon n, this particular sequence, is a decreasing sequence. And in fact, I've shown you this, that n raised to power, okay, so, n raised to power 1 upon n converges to 1. In general, always remember n raised to power 1 upon n would be what? It is 1 raised to power 1, 2 raised to power 1 upon 2, 3 raised to power 1 upon 3, 4 raised to power 1 upon 4, so on and so forth. And you would be, one can identify from here that n raised to power 1 upon n is always greater than equal to 1 for all n belongs to natural. Okay, this is something that I'm doing it for you again. I have done it for you. So n raised to power 1 upon n can be approximated by 1 plus some number, let's say Rn. And as n tends to infinity, I'll prove that this Rn tends to 0, which means that n raised to power 1 upon n, the limiting value is 1. So let me see how. So here it is. I'm doing it for you here. N raised to power 1 upon n is equals to 1 plus Rn. And if I do this, it is 1 plus Rn raised to power n. And so n is equal to 1 plus n times Rn plus n into n minus 1 upon 2 factorial Rn whole square. And from here, it's clear that n would be greater than n into n minus 1 upon 2 Rn square. And from here, it is clear that Rn square will indeed be greater than 0, but less than 2 upon n minus 1. As n tends to infinity, Rn tends to 0 by Sandwich theorem. So as n tends to infinity, this Rn tends to 0 implies what? It implies that n raised to power 1 upon n, the limiting value for this is equals to what? It is equals to simply 1. So from here, if I want to find summation n raised to power 1 by n minus 1 raised to power n from n equal to 1 to infinity, it is quite evident from ratio test, from root test, that this is equals to this, certainly 0, it is certainly less than 1. So from root test, it is quite clear that this series given to you is a convergence series. It is a convergence series. I hope it is clear. Now let us do a simple problem. Okay. Now we want to investigate the convergence and divergence of this series. How to do this? See, I know that if log is here and 1 by n is here, and if I try to differentiate it, I will get cos of 1 by n and then minus 1 upon n square. So my strategy would be to compare ln of cos of 1 upon n by 1 upon 2n square. Okay, let me compare. So in comparison test, what we do, we take the limit. As n tends to infinity, this goes to 0, and as n tends to infinity, this goes to 0. Cos 0 is 1, log 1 is 0. So what I'll do, I'll use L'Hospital rule. So this will give me 1 upon cos of 1 by n times sine of 1 by n, and 1 by n square is minus 1 upon n square. And here if I do it, it will be minus 2 upon 2. Okay, this will be minus 2 upon, okay, this is fine. Okay, so eventually what I'll get, I will get tan of 1 upon n with a negative sign. Okay, so sorry, negative would come here. Okay, so negative would come here. So sorry, so this would be like positive. So the question states that there is negative here. So this would be tan 1 by n, and there is a negative here as well. So this negative cancels out. So this is tan 1 upon n, and times 1 upon n square, and then times n cube. So what you are getting that limit n tends to infinity is simply n times tan of 1 upon n, or I can write limit n tends to infinity tan of 1 upon n upon 1 upon n. Okay, and this is certainly equals to 1, which is certainly non-zero value. And if it is a non-zero value, then it implies what? It implies that this particular series, that is summation minus of log of cos of 1 by n, behaves the same way as summation 1 upon 2n square. So this is convergent, implies this series is convergent. I'm so sorry for this. This is negatively written. So therefore, this series is convergent. Okay, so this is a good question. Now let us do one more question. What do you think can be stated about this series? what can be stated about this series? See, now this particular series converges when? Let us examine that. So if I do this thing, if I take n common here and n common here, so I'll get n raised to power 2n. So this will be 1 upon 1 plus a upon n raised to power n plus b. I will get n ki power n that I've already cancelled. So I'll get n raised to power b times here I'll get n raised to power a, and I'll get 1 plus b upon n raised to power simply n plus a. So sorry about it. Okay, so what I've taken n common out, and this is something that I've got now. Now as n tends to infinity, 1 plus b upon n raised to power n into 1 plus b upon n raised to power a. This will certainly go to 1 because as n tends to infinity, this is going to 0. 1 plus something tending to 0 raised to power a finite power. This is 1. However, this will go towards e raised to power b. And similarly, this in the limiting case, this will go towards e raised to power a. So what I'll do, I'll compare this particular given thing by this thing. So n upon 2 ki power n upon n plus a raised to power b times n plus b raised to power n plus a, sorry. This is equivalent to writing this, which is 1 upon 1 plus a upon n raised to power of n plus b times n raised to power b times n raised to power a times 1 plus b upon n raised to power of n plus a. So what I'll do, I'll divide it by 1 upon n raised to power a plus b. Now this particular series converges if this particular series converges. So it implies that the given series, which is summation n raised to power 2n upon n plus a raised to power n plus b times n plus b raised to power of n plus a converges only if 1 upon n raised to power a plus b converges, and which will converge only if a plus b is greater than 1. Okay, now let us do last question in this particular scenario. What do you think about this series? Summation n equals to 1 to infinity e raised to power a upon, sorry, a ln n plus b upon c ln n plus d, where a, b, c, d all belongs to R. What do you think about this series? See, if now here arises a few cases, let us take it case by case. So let us take the first case. If c is let's say non-zero, because if c is 0, then this series could be like if c is non-zero. And first taking the case if c is non-zero. Now if c is non-zero, then just think about this. Limit n tends to infinity e raised to power of a ln n plus b upon c ln n plus d can be written as limit n tends to infinity e raised to power a plus b upon ln n and c plus d upon ln. What I've done, I've just taken ln n common from numerator and denominator. As n tends to infinity, this goes to 0, this goes to 0, so you will get e raised to power a by c, and which is certainly non-zero. So clearly, if c is non-zero, then the series is divergent. Then this series e raised to power a ln n plus b upon c ln n plus d is divergent series. Anyway, okay, this is the case one. What if c is equal to 0? Now there lies a little bit of possibility here that if c is equal to 0, then what happens? So if c is equal to 0, then what happens? Then this thing is equals to, I'll write it one more. Okay, so if c is 0, this reduces to writing a raised to e raised to power ln n plus b upon simply t. Okay, now if A by D is equals to 0. Now, if A by D becomes 0, then it becomes e raised to power B, certainly non-zero, and which would imply that summation series, let's say this is Sn, I'll write here. So this summation Sn is divergent because it does not hold the condition for the convergence. Because if the series is convergent, then limit Sn should be 0, which indeed is not the case. So if A by D is 0, then it is not working. If A by D is positive also, then also it's not working, because if A by D is positive, then e raised to power A ln n upon D times e raised to power B. If I write this way, as n tends to infinity, this would go towards infinity, claiming that summation Sn is divergent. Please do remember what is Sn. Sn is this fellow. I don't want to write it time and again. Now, if A by D is non-zero, if A by D is minus of 1, okay, if A by D is minus of 1, then what happens? And if A by D, uh, if A by D is, if A by D is less than 0, then what happens? Okay, so basically, if A by D is negative, if A by D, so if A by D is negative, then what happens? Because there lies a little bit of possibility. However, don't take it this way. See, summation an is convergent implies limit an is 0. Limit an 0 does not imply that summation n is convergent. Okay, so now I'm taking the cases if A by D is less than 0. So if A by D is, so if C is non-zero, clearly series is divergent. If C is equal to 0 and A by D is greater than equal to 0, series is again divergent. Now what I have to do, I have to take the case A by D less than 0. So now consider the case that A by D is less than 0. And this is the series. This is the series. If A by D is less than 0, then what happens? Now, if I take, C is 0. So if C is 0, so this I don't have to take. So if A by D is less than 0 and C is equal to 0. So this is like equivalent writing A raised to power. Let us first write it in a little bit easier fashion. So it is equivalent to e raised to power ln of n raised to power A by D and this into e raised to power B by D. Now you see, this will be equivalent to writing n raised to power, because this is log EE. So this is n raised to power A by D times e raised to power B by D. So basically, if C is equal to 0 and A by D, if I'll take negative later on, but in general, this series reduces to writing 1 upon n raised to power minus of A upon D. This is constant, just forget about it. Now this is convergent only if minus of A by D is greater than minus of 1. Minus of A by D is greater than 1. That implies A by D should be less than minus 1. So only if A by D is less than minus 1, then it will converge. If minus of A by D is less than 1, that is, if A by D is greater than minus 1, the series diverges. In fact, even equals to 1 also, this series diverges, because if A by D is equal to minus 1, this series would be 1 upon n. So clearly, if we want that this series summation n equals to 1 to infinity e raised to power A ln n plus B upon C ln n plus D. If we require that this converges, the condition is that C should be equal to 0 and A by D must be less than minus 1. These are the conditions for the convergence of the series. So I hope you might have learned a lot from this lecture. Please do stay connected. Till then, take care. Bye-bye.